In this video, we're going to be talking about the SMA, WMA, and EMA for trading from a digital signal processing standpoint. We're going to be doing our analysis in Python, and at the end of the video, I'm going to be giving a comparative analysis between the different filters, what their pros and cons are, and providing some ways for you to visualize the different aspects of the filters. Alright, so here I've hopped into VS Code and I'm in a Jupyter notebook. I originally planned on kind of writing through this process as I went, but it ended up being quite a bit, as you can see, and so I think it's better to just kind of walk through it instead of writing the code out manually. And we'll jump right into the simple moving average filter and how it works. So from a digital signal processing standpoint, what we need to know is the period. I've also created this variable here called the Nyquist frequency, and this is the highest frequency that we're ever going to be measuring. So for trading, it's always going to be 0.5. There are no frequencies that we'll ever encounter that are higher than 0.5 bars. Then we're also initializing some variables for SymPy, and we're going to be using those pretty much right away. So if you remember from the Fourier transform in the previous video, we need a complex exponential. And so that's what this is here. The only major difference is instead of frequency, I'm using period, which is a little bit easier to think about sometimes. Now we need to take the Fourier transform of it. And so for the SMA, this is what the Fourier transform actually looks like. We're going to integrate from 0 to w of the complex exponential. And that's all going to be multiplied by 1 over w, because you know that the width of our window, or the period of our SMA, the filter coefficients are 1 over n, but in this example we're just using w instead. I know that's kind of confusing, but when I originally wrote this out, that's how I did it. So then we can integrate that function, and you see we get this. And from here, now that we have this this impulse response, we can start looking at the frequency spectrum for this filter. So you can see now we're plotting the impulse function here. So we get an array out that is equal to all of the, I'm calling this P sweep. This is all the periods that I want to look at. And the phase, if you remember, is the arctangent of the imaginary component over the real component. And then in NumPy, we're always in radians, so I'm converting the phase to degrees just so it's easier to understand. The next thing I'm doing is I'm creating an interpolation function for the phase. This isn't very important, but I was using this for something. So you can test, you can say throw in a 16 bar period and see what the phase is, and the phase is 67 degrees for a 10 bar SMA. The next thing I'm doing is plotting the frequency response. In the previous video I showed this in decibels. This plot is just going to be the magnitude. It's a little easier to look at. This is more of like a volume slider from 0 to 1. So instead of the cutoff being at -3 decibels, in this case it's somewhere around 0.7. And that's just when you take the log base 10 and multiply it by 20, you get -3 when you put in 0.7. So that's what that's about. And then notably here you'll see the poles of the filter, right? And so these are those frequencies that I was talking about, where those frequencies are completely eliminated from the response, which is interesting with the SMA because it's not really in the WMA or the EMA at all. And so what do I mean by those frequencies are completely eliminated? I'll go ahead and show you here. So in this other notebook, I'm just going to do some standard imports, and I'm going to generate a synthetic price signal, so just something fake so that we can look at it. And so what I'm doing is I've got time, and so I'm creating 200 bars, right? And then I'm going to go ahead and create some trend components. And these are components that have a really long cycle period, and they have really high amplitude. You can see this one I've given an amplitude of 200. This one is an amplitude of 25. And then the period here is 300. So a full cycle would be 300 bars. A full cycle would be 100 bars for this one. I am introducing a random phase shift. You can kind of ignore that. That's just kind of for fun, so I can generate different random signals. You'll notice I'm taking the sine or the cosine of that. It doesn't really matter. Both of those are going to create an oscillating wave. And so the outcome of this is basically we're creating a fake price series that has specific frequency content in it that we want. And so if we go back to our filtering thing, you can see right here that we've got a cycle, a pole at 2 bars. There's a pole at 2.5 bars. There's a pole at 3 1/3, and then I think it's 5, and then 10 bars. And so what I've done is I have created cycle components, and these are higher frequency and low amplitude, just like a price series would be, right? You have a bunch of high frequency noise going on, and I've made those cycle components all have those frequencies corresponding to the poles of the SMA filter. So in theory, what should happen is these cycle components, since they all line up with these poles, they should get completely eradicated from the SMA filter, which is interesting. So you can see I've got all of those cycle components there, and then our full price series, I'm just calling it cycle, is just the sum of all those. Oop, looks like I need cycle 5 there. So I'll run that, and I've got the cycle. Oh, I've got to import. So I've got the cycle, and then what we want to do is maybe just look at the cycle only, right? And so there it is. So you see we've got this, lower frequency, high amplitude moves, right? So these are like trend moves. And then we've got a lot of high frequency, low amplitude stuff going on here. And usually we're trying to filter this out when we're trading. And so let's just look at the trend components. So if we plot the trend component, you can see that the trend component is actually quite smooth, right? So that's that low frequency stuff. There's not a whole lot of noise going on. And the oscillations are all at a really long time scale of, in this case, 300 bars and 100 bars is in there. What we want to do is maybe look at what the cycle components look like. And there you see them there. So you can see we're basically just overlaying this noise that has a specific frequency spectrum onto our trend. And now if we want to just look at our SMA, you'll see we've got our SMA filter now in orange, and you'll notice that it's actually very smooth. It's exactly the same amount of smooth as the trend component, and that is the elimination via the poles of the SMA filter that's going on. If we zoom in down here, we know from the previous video that we should have 4.5 bars of lag, right? So let's zoom in a little more. You can see we're at maybe bar, 135 here. And then over here, we're at bar, it's somewhere around here, like 140 or so. So that kind of lines up with the 4.5 bar lag that we expect for a 10 bar SMA. So you might be wondering, different is a 10 bar SMA from a 9 bar, right? Because the 10 bar has those specific poles that are going to eliminate those specific frequency components that we want. And if I change this to 9 here, you'll see something interesting. You'll see that it immediately becomes noisy, right? And that's because the 9 bar SMA has different poles than the 10 bar SMA. Now, in certain applications, having poles in the filter like this may actually be a good thing. And in John Eller's later books, he does devise some filters that have poles at specific points to eliminate certain frequencies. But a lot of people, in DSP seem to not really like the SMA filter for this reason, because if you can get some noise going on in there when you don't want it, if you don't have the perfect arrangement of the poles or whatnot. So that is what I mean when I say that at these pole points, the frequencies at those points are completely eliminated from the filter response. So the other thing we have here is the phase response. This is a little challenging to look at because when we take the arctangent, this only returns an angle between 0 and 90 degrees. And so we need to unwrap it so that we get the full 360 degrees of the circle out of it. So now that I've showed you kind of the hard way of manually taking the Fourier transform, I'm going to show you the easy way, right? And from now on, we'll probably just look at the easy way of doing this for the sake of time. But I will provide this code in the description below so you can play with it, or if you want to read through all of this theory and stuff, you're free to do so. So the way we're going to do it in the easy way is we're going to import this function freq_z or frequency z from SciPy. And what we're going to do is we're just going to pass our filter weights to this function, or our filter coefficients, right? And so for an SMA, we know that it's 1 over n, or 1 over the period. And with a period of 10 in this case, each of our filter weights is going to be 1/10, right? So I'm just creating a list of 1/10, a 10-element list of 1/10, right? And what I'm going to get out is our frequency and our response, which is h. So from that we can get the phase, which is the imaginary part over the real part of the response, or the arctangent of that. The normalized frequency is simply our frequency over 1/2, and then our magnitude, as you know, is absolute value of h. And then I'm doing something similar with the phase. I'm unwrapping it first. So we talked about how this should all line up really. So NumPy has a nice function called unwrap, and you pass in the period of pi, and you'll get a nice array out that has been completely unwrapped and put together. So if we go ahead and plot that, you'll see this is the same exact thing as I plotted up here, right? Except I'm plotting it in decibels this time, and this is the plot that I used in the video. The next thing we'll do is the phase delay. So phase delay is negative of our phase divided by the frequency. And I'm not going to go too hard into why I've got to put 2 times pi underneath there, but there's our phase response from the video. In this case, what we're looking at is the lag time in bars of the SMA filter at different frequencies. And we know that the SMA always has a constant phase delay across all frequencies. So no matter what frequency we're talking about, we always have a 4.5 bar delay. All right, so that is the simple moving average. The weighted moving average is a little bit more complicated, and I'll stop by just showing you the Fourier transform and how it's a little bit more complicated. And I don't know if I could solve this by hand. Maybe I could, but I don't really care to. The other thing I do in here is, if you're interested, I develop an empirical relationship for the cutoff frequency for the WMA, because that does not have a closed form cutoff frequency expression that I know of. And actually I did make a mistake in the previous video, so I'll throw up the old slide right now, and with the updated expression for the WMA. I'm not sure what I was doing when I typed that into PowerPoint, but this video has the correct one, and I've tested it and it's correct. With the WMA impulse response, we can do the same thing where we integrate it, manually. We plot it out, and we get this nice kind of wavy filter response, which is interesting. And I should note that this is actually a 4-bar weighted moving average. So I'm kind of switching it up. And this one has some poles in it, right? And the poles are these low points, but the poles are not complete eliminations of those frequency components like it is with the SMA. So you notice that it's a little bit, less violent of a response, which is good. We still get this kind of jagged response, but it's got some character to it compared to the SMA. Now the easy way, again, this is probably where you should focus, because most people, if they're doing filter analysis, they're going to be using these pre-built functions. They're not going to be trying to kill themselves with, SymPy. So for this, we know that the filter coefficients are simply, I've created an array, 1 to the period, so it would be 1, 2, 3, 4 in this case. And for each of those, it's 1 over the sum of all the periods. And so 1, 2, 3, 4, what is that? It's 10. So it's 1/10, 2/10, 3/10, and 4/10, and that's our filter. I can go ahead and create the lag here. I'm not going to worry about that. We're passing our filter into freq_z, and we get our response out just like the SMA. And you see it looks exactly the same as the manually brute force method, right? And I've also plotted here the cutoff frequency. So this point is the point at which frequencies beyond it are reduced by more than half their power. So we can also do the phase response or delay, this phase delay right here. So you can see what we've got here is we've got our normalized frequency. So highest frequencies over here, low frequencies over here. So trend is over here, noise is over here, right? And you can see that high frequencies has really low lag. It has 0 lag, right? And that kind of makes sense, right? Your filter is your weighted moving average and stuff. It's reacting pretty much right away to movements in the price. Whereas longer cycle components, so lower frequencies, longer cycles, they have more lag, right? So they're out here at 2 bars of lag at infinite cycle. So if you have 2 bars of lag, you might think, well, that's not very good. But in reality, think about a 100-bar cycle. What's 2 bars of lag? It doesn't mean anything to you, right? So here in a little bit, we'll put some of this into perspective, because I think looking at this, interpreting this isn't very intuitive. So let's move on to the exponential moving average. If you remember, the exponential moving average is not defined by bars. That's a mistake, sorry. And what we have is an alpha parameter instead. And so in this case, I'm just going to be testing an alpha of 0.25. Similarly, we've got some variables for SymPy because I also do a brute force. I'll go down just to show you the look of the Fourier transform. So this is what it looks like before you go ahead and integrate it. It gets pretty ugly, as you can see. And so this is something that I would love to solve numerically, so I don't have to look at this. But I'll skip that. Well, maybe I'll show you the plots, right? So here is the frequency response of the EMA and the phase response. And one thing you'll notice is we get a pretty immediate drop off compared to the WMA and the SMA. And what that means is that we're getting more smoothing out of the EMA than either the SMA or the WMA. And we're usually doing it with less lag, right? So, or for a given level of smoothing, you're going to have less lag with an EMA, right? So, again, I think this is kind of a short period EMA, but it's neither here nor there. So we can do the response with freq_z. In this case, you'll kind of refer to the equations that I provided in the previous video, but the filter coefficient is simply 1 minus alpha raised to the ith power. Here, I'm only taking the filter out to 100 terms. You know, in reality, the EMA is an infinite impulse response filter, so you actually need to do like 1e to the 10 or whatever, you know, but 100 terms is just fine. You don't need to kill yourself again. So again, we're computing the phase in the same way, calculating the critical frequency here using that same equation that I provided. The frequency response looks exactly the same. Phase delay, same as before. We're plotting the number of bars of lag versus the frequency. See, again, really high frequencies, we get almost no lag, right? So immediate response, right? Low frequencies, we get 3 bars of lag. So let's get into a little bit of a comparative analysis between these filters. So the way that I'm going to do that is I'm going to establish a lag level. In this case, 10 bars. I'm going to say we can accept 10 bars of lag. And then what I'm going to do is use those lag equations from the previous video to calculate what the equivalent periods are for each of these filters that provide that level of lag. So in this case, I'm saying I can go with 10 bars of lag, and let's figure out what the periods are for those. So for 10 bars of lag, we need a 21 bar SMA, a 31 bar WMA, and an EMA with an alpha of 0.091. In reality, it's 0.090909, but we're just rounding it here. We can create the filters like we did before, the filter coefficients, and we get the responses out from SciPy, and then we're getting the magnitude again because we're going to compare the responses for all these. Similarly, I'm getting the cutoffs, the cutoff frequencies, so I can plot those. And just printing some stuff out here, we don't need that. And the next thing is the plot. So here's our comparison of the frequency response. I'll remind you, all of these have the same lag, right? So what we're looking at here primarily is that these points kind of are spaced out. These points are the cutoff points. The cutoff point is the point where frequencies beyond this point are reduced in power by more than half. So if we have a point that's farther to the left, we're getting more smoothing. We're cutting out more frequencies, right? Because this is all of our high frequency content over here. And so if we move this dot to the left even more, we're cutting out even more high frequency stuff, and we're just getting trend components. We're just getting the components that we want out of it. You can see the WMA is closer to the EMA in terms of smoothing performance, and the SMA is out here. It's the worst of the bunch in terms of smoothing, but it does have certain benefits that I'll get into. The other thing you'll notice is we got a steeper drop off immediately up here with the EMA than either of the other ones, and again, that's going to be providing an extra little level of smoothing. We can get a table of all of these lags and cutoff frequencies here for your reference, so you can see we've got increasing lag here, right? So you pick a lag level, and then you can read off the SMA, WMA, and EMA periods that will provide the same level of lag. And you get the cutoff frequency for each of them as well. So again, the cutoff frequency is, say you pick an SMA with a 35 bar lag, 71 period SMA. It's going to have frequency components that have cycles shorter than 155 bars are going to be attenuated. They're going to be reduced in volume. They're going to be smoothed, right? So that is a problem if you are trading, for instance, a 50 bar cycle. So if you wanted to trade a 50 bar cycle, you would not pick a 71 bar SMA. In parentheses, I'm just plotting the actual level, the actual decimal calculated period or cutoff, but I've just rounded it. Now we'll talk about maybe a better way to look at this information, because people don't really look at a table of values and be like, oh, I get it, So let's look at it in a different way. And so what I'm going to do is I'm going to plotting the lag as a percentage of the cycle that you want to trade. So how this works is you pick the cycle that you're going to trade. So say you're like, I'm going to trade a 100 bar cycle. So that means the price goes down and up in 100 bars, or up and down, You're trading a 100 bar cycle. Then you say, okay, what SMA do I want to use as a part of my strategy for trading a 100 cycle period? What's going on here is you'll notice that if you pick a really low period SMA over here, so below 25 or so, you're getting a lag that's less than 1/8 of a cycle, right? And so 1/8 of a cycle is this point right here, so 1/8 of the cycle. If you wanted to be in your trade around this point or better in the move, you can only go to 25 bar SMA, right? If you're trading 100 bar cycle and you decided to pick, for instance, a 100 bar SMA, well then you would be getting in at a half cycle lag. So that would be here, right? So you're trying to get in up here and capture this down movement, right? But you're using 100 bar SMA, which has a half cycle lag for a 100 bar cycle. And so you would basically need to reverse your trade logic, right? And you'd need to say, okay, I'm going to buy when the SMA is telling me to sell, right? So you got to be careful about how you pick these things. So on this chart, I've got plotted out the 1/8 cycle line, the quarter cycle, half cycle, and full cycle. Full cycle of lag is obviously worst case scenario, right? So let's say, for instance, you're trading a 50 bar cycle and you're going to use a 100 bar SMA to trade it. That means the information from this point, if this is our price, the information from this point will not get to you until here, until all the way over here. And that would be a full 50 bars. And if you're trading the daily, that's a month and a half. So you're a month and a half late to the trade, right? So that is that. We'll look at the WMA, same analysis. And what's nice about the WMA is you'll notice that these lines have spread out farther to the left. And that means we're getting more bang for our buck in terms of lag. I mean, we already knew that the WMA has a better lag profile than the SMA, but this kind of really puts it into perspective. So let's use our 100 bar cycle that we're going to trade example again. And so for this, if we want an 1/8 cycle lag or less, we would pick a WMA with maybe, a 30 to 40 bar period. So 30 to 40 bars versus 25. So we're getting more smoothing with that larger filter with the SMA, but we're not sacrificing our lag, right? We're still getting a better response. One thing I do want to point out about cutoff frequencies is you'll notice that the SMA and the WMA have lower cutoff frequencies or lower cutoff periods, And so this can be advantageous if you are trading in a situation where you want as much information as possible, right? You don't want to smooth too much stuff out. So that is where the SMA and the WMA is stronger than the EMA, is when you are looking to retain some information. So maybe you're willing to sacrifice a little lag, but you get a little less smoothing and you get a little more information out in the SMA or the WMA than the EMA, because the EMA has got really high smoothing. So I know that's kind of a lot. It's a lot to absorb to kind of look at this stuff, but I think if you spend some time with this, download the code and go through it and look at it, or even just take a screenshot of this chart here for WMA or for SMA, and this can really help you kind of decide what filter you're going to use. And if you have a strategy where you're looking at certain cycles, certain trend lengths, and you want to kind of time your entry based on an SMA or a filter of some sort, you maybe want to consult a chart like this or do some math to figure out what filter length you want to use so that you're not missing out on information or you're not filtering out information you're looking for. And so I hope you guys enjoyed the video, and stay tuned for the next one.